Today we study X28Q, the second law of thermodynamics. The problem 1, in previous class we have shown the entropy change delta S of an ideal gas consisting of n molecules from the initial state to another state. As you know, because of the equation PV equals n kBT, only two variables are independent. So here we have chosen the volume and temperature to be the independent variable. Then the pressure is nkBT over V. In that case, according to our derivation, the delta S, a change in entropy from the initial state to a final state, is expressed like this. Compute delta S during the free expansion from V0 to NV0. And in free expansion, the temperature is invariant. The gas sample does not work. Heat transfer is not allowed. Hence, the temperature is invariant. T and T0, they are the same. So this part is to be removed. This is trivial. And then we have only volume change. We have logarithm. According to the statistical definition of the entropy, is a multiplicity, log multiplicity, and the scale is Boltzmann constant. Okay, using this definition, we would like to check our derivation is equivalent to the Boltzmann's statistical expression for the entropy using multiplicity. We call delta is S minus S0, the multiplicity of the final state divided the multiplicity of the initial state. Here, this is not pressure. It is probability. So probability is proportional to the multiplicity. So what we can find is why don't you choose V0 and the initial state has only a single beam, and in the final state we have n identical beams, n partitions, and we have capital N molecules. For given molecules, we have a multiplicity to choose these 1, 2, 3, 4, n beams. So we have multiplicity n for each molecule, and every molecule is independent. Therefore, we have small n to the capital N multiplicity for the distribution of capital N molecules inside small n. Number of beams is small n. As a result, we find that this probability is a KB log multiplicity in comparison with the initial state that has only single beam available. After the expansion to n beams from V0 to n times V0, we have a multiplicity of order small n to the capital N in comparison with this, only a single beam to the capital N. And we have a ratio of multiplicity of the final state in comparison against the initial state. It is n small n to the n. This is the result. So we think this entropy change computation with the thermodynamic variable and the statistical approach by Boltzmann, they are equivalent. Number 2, the previous class we used the pressure and volume. In the previous page, we used the volume and temperature as an independent variable to find out the entropy change from the initial to the final state. Entropy change from the initial to final state can also be expressed in terms of pressure and volume. And if we make use of pressure and volume, the power will be the heat capacity at constant pressure and heat capacity at constant volume. We can also pull out this CV out of this logarithm, then the ratio appears in the powers of the volume ratio. So here, gamma is the Cp over Cv. In an adiabatic process does not give and take heat. Entropy change can be computed by making use of thermodynamic definition, the delta Q equals 0. The entropy change is exactly 0 in this case. Number 3, consider the Carnot engine whose PV diagram is shown below. This is Carnot engine consisting of a constant temperature processed at hot region in contact with the heat reservoir at high temperature. The gas expands and it does work, and it accepts the heat and does work, and then it makes a further expansion without accepting any heat from the environment. Instead, this gas carries out a work that does a positive sense as a result without accepting any heat. So from B to C, its temperature is going down to arrive at the low temperature. And at low temperature of heat reservoir, it shrinks the size and the work done by the system, and it loses a heat, and the work done by the system is all negative. And then it experiences another adiabatic process without exchanging any heat to arrive at the initial state. And it is a kind of loop, return to the same state, and it is a cyclic process. Because this cyclic process is rotating clockwise, the net work done by the gas during a single cycle is the area inside the closed path. And we recall that the pressure and volume has some relation as a constant when we multiply pressure multiplied by volume to the power of gamma. That is Cp over Cv. Compute the entropy change delta SH in a isothermal process A to B. This is accepting heat, so entropy will be increasing at the temperature at TH of the Carnot engine, during which the heat is accepted by the engine. Compute entropy change at SL, and we return to the same place. So entropy change can also always be computed in terms of the thermodynamic variable PVT. Any two of PVT will determine the entropy change. However, the initial state and the final state, they are exactly the same, and without computation, we expect that they are canceling each other, so the delta S in total must be 0. Well, we'd like to check if it is true. SH is the dq over T at high temperature. Because temperature is fixed to be an isothermal process, we have TH pulled out of the integral, and this is simply QH over TH. We put the positive sign to be the QH because it accepts the heat at high temperature. At low temperature, the same is true, but the QL is is giving away to the environment that the QL is negative. Therefore, QL is replaced with minus absolute value of QL. Using the information for the volume and initial volume V0, and we substitute the result in here to find out the change in entropy. Finally, QH and QL are expressed as this. This accepting heat and A to B. Heat, it accepts the heat, but temperature is fixed. So accepted heat is completely transferred to the work. Therefore, the accepted heat at high temperature, fixed temperature at TH, it does not increase its own energy. Instead, this heat is completely transferred. In a similar manner, when it shrinks from C to D, it's giving away heat is exactly the same as the work done by the gas that is negative. As a result, we can compute this one in terms of the constant temperature condition. We have pulled out the constant temperature and NKBT factor, and becomes it as a logarithm integral. So initial to final. So we have a log VB over VA and VD over VC. A, B, C, D. As a result, we find that at high temperature, delta S change is from VA to VB, VA to VB. The heat is completely transferred to the work, and temperature is fixed, so the temperature cancels, and finally we have this kind of form. Again, we have this constant temperature process at low temperature. It is a negative definite, and again that is involved with the logarithm of the ratio of the initial to final volume. If I add these two contributions all together, because of this negative sign, this VC and VD, they are to be extended, and we have VB over VA, this, and then this is to be multiplied to the argument. Finally, because the entropy change doesn't happen here, no entropy change, because the dq is always a zero in an adiabatic process. These two contributions, positive contribution, negative contribution, they cancel to arrive at the same state. This requirement will give this is unity, right? Only if it is a unity, this logarithm becomes a zero. So A, B, C, D, they have a relation. This, because PV equals NKBT, it's from A to B, it's a constant temperature at TH, A to B, A to B, A to B, at TH. So they are constant, so PV is constant. So PV constant. And here, C to D, is low temperature fixed to the TL. And again, the product of Boyle's law, the product of pressure and volume, is always constant during a constant temperature process. As a result, this relation is again expressed in terms of the pressures. Okay, that's it for today. Thank you.